Alright, hello everyone. I hope you guys are doing great. So today we are going to be doing the solutions to CodeTon round 5, and this round was held yesterday, so I am a bit late, but I guess something is better than nothing. So we'll anyways be doing the solutions, and we'll be discussing the first 5 problems today from A to E. Okay. And talking about the round, I think this was a pretty good round. There were like pretty much no surprises. As you can see, the number of solves decreased gradually as they should. There were no huge difficulty gaps as well. There were no huge difficulty jumps as well. So yeah, I would say overall a pretty decent round. The first 3 problems were as they should, like they were pretty doable by someone who's rated around 1400 1500. And problem D again was also pretty nice, so I would rate it around 1900 or so. And again, problem E was really interesting, and even though the code is really small and the code is really short for problem E, it required a lot of thinking, at least by me, and I couldn't even solve it during the contest since I kept trying a wrong version of the problem. But still, I think it would be around 2200 to 2300 rated at least. So yeah, overall I would say a pretty decent round. There were some issues with the pre-tests in problem D. I mean, there were no multi-tests even in the system tests, so that led to some FSTs, around 150 FSTs. But other than that, I would say that the round was pretty decent. Okay, so we'll be discussing the first 5 problems, and without further ado, let's get started with problem A. So in this problem we have 2 players that are playing a game. So both of them have some monsters. The first player has n monsters, and their abilities are given by this array A of length n. The second player has m monsters, and the abilities of all those monsters are given by the array B of length m. So both of them obviously take turns and they play moves. So the first player, what he does is he basically chooses 2 monsters. One monster would be his own and one monster would be the other player's, and then these monsters will fight with each other. And basically what happens is that the monster whose health is smaller dies, and the monster whose health is bigger gets his health reduced by the health of the smaller monster. Okay, so in formal terms, if the healths of the monsters or the abilities of the monsters are x and y, then the ability after the fight will become x minus y and y minus x. But if the ability of any monster is smaller than or equal to 0, then that particular monster will die. Okay, so that's what is happening in the game. Both of the players do this turn. Both of the players have the same turn. So that's the game, right? And the game will end when at least one player has no monsters left alive. Right, so if someone has no monsters left alive, then that person is a loser. Okay, so the winner of the game is the player with at least one monster left alive. Okay, so yeah, so now if both the players have no monsters left alive, then we can say that the game ends in a draw. So if after a move all the n plus m monsters are dead, then we can say that the game has ended up in a draw. Okay, and our job is to find the result of the game, obviously, if both the players are playing optimally. So yeah, that's the problem. I would say this was a little bit tricky, but I mean not that tricky as well. So yeah, let's just discuss the solution. Cool. So the key idea of this problem is that we'll talk about the main observation. The main observation which can be used to solve this problem is that after every move, the sum of the healths of both the monsters of both the players, that sum gets decreased by the same value. So the sum of ability values of monsters of both players gets decreased by the same value. So yeah, that's what the key observation of this problem is, and this minimum value actually is minimum of x comma y. So you can see it like this. So let's say that we have 2 monsters x and y. So the person chose the monster with health x from his list and the monster with ability y from the other person's list. So let's say that minimum of x comma y is equal to m. So we can just say that after the fight is over, both x and y are becoming x minus m and y minus m, right? And the reason for this happening is that the monster whose health is M is essentially dying, so his health is becoming 0, and the monster whose health was greater than or equal to M, his health is just getting decreased by M. So we can say that the sum of the ability values of the monsters of both of the players gets decreased by M, and so we can write down this invariant. So the invariant is that the difference of the sum of the values, so the difference of the sum of the values of monsters of both the players this remains constant, because both of the players sum is decreasing by the same value. If we take the difference, then that difference remains constant. So then we can say that the person who had the greater sum initially will also have a greater sum when the game ends. Okay, obviously the game will end in a finite number of moves, because in every move at least one monster is dying and we have n plus m monsters, so the game will end in a finite number of moves. And through this invariant we can say that the person who had the greater sum initially will also have the greater sum when the game is ending. Okay, so this gives us the solution. So the solution is simple. We just compare the sums of the monsters, the sums of the abilities of the monsters of both the players, and the person who has the greater sum will be the winner, and if both of them have the same sum, then the game is going to be ending in a draw. Okay, so yeah, this is the solution. I hope this was clear. So this actually noting down these invariants is actually a pretty important skill in being a good competitive programmer. Problem A rarely involves such invariants, but you will notice that constructive problems and stuff like that, the problems in which you are given some kind of operations that need to be performed, and you need to convert a string s to a string t, something like that. In problems like that, noticing the invariant is a very, very important skill, I would say. And yeah, so it's pretty useful in competitive programming in general. So yeah, this is the solution to this problem. I hope it is clear to everyone. For the sake of completeness, let's just have a look at the code. So the code is pretty simple. You calculate the sums of the values of the monsters of both the players. If the sum is equal, then the game will ends in a draw. Otherwise, the person who has the greater sum is going to win the game. Okay, cool. I hope this solution is clear. Let's now move to problem B. Alright, so problem B is again a pretty good problem for its position. So here we have 3n books, and essentially these 3n books are arranged in 3 stacks, and each stack contains n books, right? And what we want is we want to read some of the books. Okay, and what we'll do when we try to read books is that we will choose a non-empty stack, and then we will read a book on the top of the stack, and then we'll discard that book. Okay, and we'll do this process for as many times as we want. So essentially we are taking a prefix of all the 3 stacks and we are reading the books on that prefix. Cool. So now our goal is there's also another thing happening here, which is the knowledge thing. So if our knowledge is currently U, and we read a book that has a knowledge of V, then our knowledge will become the bitwise OR of U and V. Okay, after reading the book with the difficulty rating of V. Okay, all the books have a difficulty rating which is assigned to them. Okay. So yeah, initially our knowledge value is 0, and we will read a non-empty or empty prefix from all the 3 stacks, and what we want is we want our final knowledge level to be equal to x, and we need to tell whether or not it is possible to do so. Okay, so the problem is simple. You have 3 stacks containing n books each. You will choose some maybe non-empty prefix from each stack, and you will read some books, and finally you will take the bitwise OR of all the books that you read, and you need to tell whether or not it is possible to have a bitwise OR value of x. Now obviously there is a very naive solution in O of n cube time, where you try out all the n cube prefixes that you can read, but that will obviously time out because n is pretty big. So let's see how we can solve this problem. So in this problem, what happens is that we need the bitwise OR to be exactly equal to x. Okay, so it makes sense to divide all the bits from 0 to 31. So 10 to the power 9, so 31 is enough. So we'll divide all the bits from 0 to 31 into 2 groups. Okay, so the groups which have the bits which are set in x is said to be the good group, and the other group is said to be the bad group. Okay, so let's call the bits that are set in X as good and the other bits as bad. Okay, cool. So an observation that we can make straight away is that we can never read a book that contains a bad bit. Okay, so we can never read a book that contains a bad bit. Okay, the reason for this is that as soon as we will read a book that contains a bad bit, the bitwise OR that we are maintaining, that is our knowledge level, that will have that particular bad bit as set. And once a bit is set and we are doing bitwise OR with anything, then that bit can never be unset. Okay, we can always add new set bits, but we can never remove set bits when we are doing a bitwise OR. Okay, so yeah, if we encounter a bad bit, then we cannot read a book because that will make our knowledge level bad. Because that will set a bit in our knowledge level which is not set in X. Okay. Similarly, we can say that we can always read a book that doesn't contain a bad bit. Okay. So this is another claim, and again this can be proved in a similar sense. And how it can be proved is that if we are reading a book and it does not contain any bad bit, then essentially if we just read it, then it's not causing us any harm, right? We are still getting closer and closer to the bitwise OR of X, and we are not adding any of the bad bits. So there is no harm in reading it. So then we come up with a simple algorithm that is keep reading books from each stack unless you encounter a book having a bad bit, right? So as soon as you find the first book that has a bad bit, you stop reading from that stack because you have to read some empty or non-empty prefix from each stack, right? So there is the simple algorithm that you can use to solve this problem. For each stack, just iterate on all the books and find the first book that has a bad set bit and just read all the books before that. And do it from all the 3 stacks and you will get the best possible bitwise OR, and then just finally compare it with X. Okay, so that's the solution to this problem. I hope it is clear enough. Let's just have a look at the code for the sake of completeness. So the code is pretty simple. So I'm using a bitwise technique to check whether or not a book has a bad bit or not. So the bitwise technique is that the value of the book and the bitwise AND of X should be equal to the value of the book, and this essentially checks whether a book is a subset of X or not, right? If a book is a subset of X, then the bitwise AND of that subset and X is going to be that subset itself, right? So that's what this trick is doing here. So it just checks if AI bitwise AND X is equal to AI or not. If that's the case, then that means that there is no bad bit in AI. Similarly, we do this for BI and CI as well. We keep reading the books until and unless we find a bad book, otherwise we break. Finally, we'll just check if the final bitwise OR that we have is equal to X or not. Okay, so I hope this is clear. Cool. So I hope the solution is clear. Now we can move to the third problem, problem C. Alright, problem C. So in this problem, we essentially have n balls which are arranged in a line, and the color of the ith ball from the left is equal to AI. Now what we can do is we can do this following operation any number of times. So we can select a range I to j, and we can select this range only if I is less than j and AI is equal to aj. Okay, so we'll choose a range I to j such that I is less than j and the color of the balls I and j is the same. And then what we'll do is we'll remove the balls from AI to aj from our array, and then essentially we'll just join the 2 parts that we get. Okay, and then we get a new array, and we continue to do these operations on the new array. Okay, so yeah, that's what is happening. We select a range such that both the endpoints have the same color. The length of the range should be strictly greater than 1. Then we just remove that range, and then we join the 2 parts that we get after removing that range. Cool. So now what we want is we want to know the maximum number of balls that we can remove if we do this operation the way we want. Okay. Cool. So yeah, that's the problem. I hope the problem is clear. Now let's look at the solution. So in problems like this, the first thought that comes to my mind is to somehow use dynamic programming. Now you might ask that why is it that the first thought that came to your mind is dynamic programming? Well, the thing is that this problem actually, if you think about this problem, you would realize that for each book you will have two choices. Either you not do an operation with that book or you do an operation with that book. Okay, so in problems where you have such kinds of choices, then dynamic programming is something that can be applied. Okay. That can be something that you can think about while you are attempting it for the first time in a contest, right? So yeah, that can be your first go-to strategy, and for this problem it worked out. So yeah, we are going to be using dynamic programming to solve this problem in a nutshell. Okay, so what we'll do is we'll define a dp of I is the maximum number of books that we can remove if we only consider the prefix I. So if we only consider the first I books, so it's a simple one-dimensional DP, nothing fancy going on here. Okay, so if we just find out this DP somehow, then the answer is going to be nothing but DP of n. So that's the maximum number of books if we consider all the books, right? So that's our answer. Cool. So now how do we do transitions and how do we calculate the DP values? That's the question that we have. Cool. So essentially what happens is that there are two cases. So the first case is pretty trivial. The first case is that we do not remove the ith ball. So what if we do not remove the ith ball? In that case, we can just say that dp of I is equal to dp of I minus 1, because we are not removing any extra balls. So we are not removing the ith ball. So we can just go to the prefix I minus 1 and check how many balls we can remove from that prefix. So cool, that's the first case. So now let's come to the case when we do remove the ith ball. Now when we do remove the ith ball, let's see what's going on. Okay, so let's see what happens when we are removing the ith ball. So we have some balls, right? So we have some balls arranged here. Let's say that this is the ith ball that we are talking about. This ball has a color of X, and there are a few other balls that are colored in color X. Okay, let's say these are these balls. Okay, so now when we are removing the ith ball, we are essentially matching that ith ball with some of these balls, right? We'll match it with one of these and then remove it, right? So that's what we need to do. Okay, so that means we have certain choices. So we can either match this ball with this ball, we can either match this ball with this ball, so on and so forth. Okay, now what happens when we match this ball with this ball? So you might argue that even though we are removing this ith ball, it can be the case that the first operation that we do is not this one. Let's say in the first operation we take this array, or in the first operation we take something like this and remove it. But my claim is that it doesn't matter. The order of these operations do not really matter, because essentially when you match both of these, now when you match these two, then this entire thing is anyway going to be destroyed, right? So even if in the ideal case you first match these and then you match these, it doesn't really matter, because if you are matching a bigger range and if you are destroying a bigger range, then the smaller range is as it is getting destroyed, right? So you can just consider that the first move that you are doing is matching this ball with something else. Okay, cool, right? Because you are matching it, right? That you know, you are for sure matching it. So if you are matching it, also you might argue that there can be some matches like this. So matches like this, intersecting matches are not really possible, because let's say you first match this range. So when you match this range, then this ball will So this ball will essentially get destroyed, so you won't be able to match this range at all. Okay, so intersecting matches are anyways not possible. Cool. So we can just consider that the first match that we make is going to be the match between two balls having color X. Now we have a choice of matching this ball with all of these balls. So now we need to decide which ball to match with. Okay. So let's formally write down what happens here. Cool. So if we try to formally write down, what will happen is that let's say we match the ball I with the ball J having the same color. Then we can say that dp of I is equal to dp of j minus 1 plus, we remove all the balls from j to I, so that would be I minus j plus 1. Okay. So this is going to be the transition, but this can only happen for all j such that aj is equal to ai. So if we try to do this naively, then this will become quadratic. So we'll iterate over all j's and we'll check whether aj is equal to ai or not. If that is the case, then we'll just do dp of I is equal to dp of j minus 1 plus I minus j minus 1. Okay. So I hope this transition is clear to everyone, because once we, let's just write it down so that there is more clarity. So let's say this is j. So let's say this is j and this is I. So once we match I with j, this entire range gets destroyed. So we start from j minus 1. So that is why I am adding dp of j minus 1. And then all of these books from I to j minus 1, these are I minus j plus 1 books, they get destroyed. So simply the transition is going to be dp of j minus 1 plus I minus j plus 1. So I hope that's clear. Now how do we optimize this? Well, optimizing this is actually pretty simple. So what we can do is we can maintain an array called mx of I. So mx of I is going to be the maximum value of dp of j minus 1 plus so even before that, let me just simplify the transition. So according to the transition, we have dp of I equal to dp of j minus 1 plus I minus j plus 1. So that is something like dp of I is equal to I plus 1 plus dp of j minus 1 minus j. Okay, something like this. Okay, so dp of I is going to be I plus 1 plus dp of j minus 1 minus j. So I have just moved around the terms here, nothing fancy done here. So what we notice here is that this term I plus 1 is constant for every I. So what we are really interested in is dp of j minus 1 minus j, and this is something that we need to maximize. Okay, so what we'll maintain is we'll maintain mx of I. So we'll maintain an array mx of I. So mx of I will store the maximum value of dp j minus 1 minus j for all indices k such that a of k is equal to I. Okay, so this essentially means that if the value at an index is I, then we'll store the maximum value of dp of j minus 1 minus j for that particular index. Okay, so sorry, not k, j. Okay, so mx of I will store the maximum value of dp j minus 1 minus j for all indices j such that aj is equal to I. Okay, and then we can essentially say that this transition is nothing but I plus 1 plus mx of ai. Okay, so if you just plug in the definition of mx of ai here, mx of ai will store the maximum value of dp j minus 1 minus j for all indices j such that aj is equal to ai. And that is exactly what we want, right? So we'll just maintain this mx array, and the transition will become dp of I is equal to I plus 1 plus mx of ai. And once we find out dp of I, we can just say that mx of ai is equal to maximum of mx of ai and dp of I minus 1 minus I. So in this way we are maintaining this mx array, and in this way we are using this mx array to do the transitions faster. Okay, so in this way we can do the transitions in constant time per index, and the problem has been solved in linear time. I hope the solution is clear. If it's still not clear, I'll just repeat it one more time. So I'll repeat it from the optimization part. So The transitions that we have is dpi is equals to dpj minus 1 plus I minus j plus 1. If we simplify the terms, we get dpi is equal to I plus 1 plus dpj minus 1 minus j. But we can do this only for values of j where aj equal to ai. So what we do is we maintain an array mx of I which will store the maximum value of dpj minus j for all the indices j such that aj is equal to I. So then we can say that this term that we are looking for is nothing but mx of ai. So the transitions will become I plus 1 plus mx of ai. Okay, and then we can just update mx of ai as maximum of mx of ai and dpi minus 1 minus I. Cool. So I hope this is clear to everyone how I am maintaining this mx array and how I am using this mx array. So yeah, that's the solution. Final answer is going to be dp of n. So let's just have a look at the code now. So the code is pretty simple, very simple. We can say that dp1 equal to 0 and dp of a1 is equal to minus 1 because minus 1 is 0 minus 1. Okay. And then we go from 2 to n and we first initialize dpi with dpi minus 1 and then we say that dpi is equal to max of itself and mx of ai plus I plus 1. And then we update this mx array as mx of ai is max of itself and dpi minus 1 minus I. Right, so the final answer is dp of n. So yeah, that's the solution to this problem. I hope it is clear to everyone. Now let's move on to problem D. So this is a really interesting problem. Let's see what this problem is saying. So in this problem we have n friends and the friends are numbered from 1 to n. Okay, and what we'll do is we'll play a lot of games and in each game we'll choose a set S which is a subset of the friends that we have and we'll play all the friends that are included in the subset. Okay, but in every subset that we choose there are certain restrictions that we need to follow. So the first restriction is that the friend 1 should be included in every subset. Okay, the second restriction is that the friend n should never be included in any subset. Okay, in every game that we play we should always include 1 and never include n. All right, so we have a third restriction which is that we are given with m additional restrictions and basically these are special restrictions and they are described by 3 integers ui, vi and yi. And what happens is that in each of these restrictions, the ith restriction we are given with 3 integers ui, vi and yi, and what that means is that suppose x is the total time that exactly one of ui and vi is playing and the other is not playing, right? So if x is the time in which one of the players is playing and the other is not playing, then that value x should never be greater than yi. Okay, this is the restriction that we have. That is that both the players like to play together. So the number of games in which one player is playing and the other player is not playing, that should not be greater than yi. So that should not exceed yi, right? Cool. So these are the set of m restrictions and these are the 3 restrictions that we have. So what we want is we want to know the maximum total time that we can play this game and we also need to construct all the games. So in the output we need to tell what is the maximum total time that we'll play and we also need to tell what subset to play in each game and the number of games as well. Also the number of games should not exceed n square. So that's also a restriction that we need to maximize the number of games, but we also need to output a solution which works in less than equal to n square games. And they have said that it is always possible. And also there can be cases when we can play for an infinite amount of time. In that case, we just need to output INF or infinity. Okay. So yeah, that is the problem. I hope the problem is clear. Just try to understand what this third point is saying. So the third point just means that the number of games, the number of minutes in which one of UI or VI is playing and the other is not playing should not exceed YI. Okay, cool. So yeah, that is the problem. Let's try to solve it. Cool. So the first thing to do is that in problems like this, when we are given with m relations between two people, we should always try to model it like a graph. We should always try to model it in the form of a graph. So that's the first thing that we should always do. Okay, so we should always try to model such problems in the form of a graph. Cool. So yeah, so that is exactly what we are going to do. But we notice that we are not just given two people in a restriction, we are also given a third number yi. So essentially it makes sense to say that we build a weighted graph, and the weights are yi, and the nodes between which the edges are drawn are ui and vi. Okay, so what we'll do is, for each restriction ui, vi, yi, we add an undirected edge between ui and vi of weight yi. Okay, so that is what we are going to do, and that is, I can say, a general blanket rule. In problems like this, you just build a graph, and if three numbers are given, then you can just consider the third parameter as the weight of the edge. Okay, so cool. Now we have an undirected graph, and we'll be solving this problem on an undirected graph. Okay, so now in problems like this, the first thing that you should do after you are done with all the preliminary observations is try to think about when the answer is going to be infinity. Or in some problems we have to output -1 when something is impossible. So in problems like that, you should always think about when the answer is going to be -1 or when it is going to be infinity. So here we are going to think about when the answer is going to be infinity, and that case again is not very difficult to think about. So let's just write it down. So the answer will be infinity only when 1 and n are not in the same connected component. Okay, so let's try to prove this. Okay, so let's say we have a graph. So let's say we have a graph which has two connected components. Okay, so this is node 1 and this is node n, and both of them are in different connected components. So what we can say is that if we always choose this particular connected component, then we are not disrupting any of the restrictions. So let's say this is component number 1, this is component number 2. If we can always choose all players in C1 and no player in C2 and keep playing. Okay, so you can see that every restriction that we have is either among players of C1 or among players of C2. There is no restriction that goes from C1 to C2. Okay, so what that means is that if we play all the players of C1, then none of the restriction is going to be disrupted, because the restriction is of the form that if exactly one of the players ui and vi is playing, then and only then the time should not exceed yi. But here we can say that all the players of C1 are playing, so that condition is never really true that exactly one of them is playing, because if there are two players ui and vi that are in the same connected component C1, then both of them are playing. Okay, and if there is ui and vi that is in C2, then none of them are playing. So it never happens that exactly one of ui and vi is playing, and that is why we can say that no condition is being disrupted at all. So instead of this time being yi, this time is going to be exactly 0 for all the m restrictions, and so we know that yi is greater than or equal to 0, so no restriction is going to be disrupted at all. So we can just keep playing this connected component containing 1, and the answer is going to be infinite. So in this case the answer is going to be infinite. Okay, cool. So with that in mind, this is the only case when the answer is going to be infinite, because now we'll construct a solution in which the node 1 and n are in fact in the same connected component, and we can always say that the number of times that we can play this game is going to be limited. Okay, so now let's see how we can say that using the first test case itself. So in the first test case, there is an edge between 1 and 3. So there is an edge between 1 and 3 of length 2. Then there is an edge between 1 and 4 of length 2. And then there is an edge between 2 and 3. that has a length of 1, and then we have an edge between 2 and 5 that has a length of 1. Okay, so this is how the graph in the first test case is looking like. This is node number 1 and this is node number n. Okay, so essentially what we can say is that let's look at when are we forced to end the game. Okay, so we can say that we are forced to end the game when some restriction is bound to get broken if we play another game. Okay, so like there is some restriction out of these m restrictions which will be broken if we play another game, right? So yeah, that is the point of time when we should stop playing, and we can say that we can no longer play the game. Okay, but this condition is exactly the same as saying a restriction containing node n will break, because if we have a restriction that doesn't contain n, then we can just play all the people from 1 to n minus 1, and that won't be affecting any of the restrictions other than the restrictions which contain n. Okay, so then we can say that we will stop playing only when we are forced to play n. So by this we can say that we will stop playing at a point of time when we are forced to play with the node number n, but as you can see, the rule number 2 says that playing with node number n is never allowed. Okay, so I hope this point is clear, that first of all we say that we will stop playing when one of this m restrictions gets broken, but if one of the m restrictions is getting broken, then we can just play all the people from 1 to n minus 1, and then none of the restrictions will be broken other than the ones that contain n, because we are playing players from 1 to n minus 1. So then we come to the conclusion that we'll stop playing only and only if we are forced to play player n. Okay, so cool. Now we look at the structure of the game. So now we will look at how the game will go. So let's look at the subset S that we will choose in each game. Okay, cool. So initially we know that we have to play with player number 1. Okay, so we have to play with player number 1. So player number 1 will have certain restrictions, right? He will have certain restrictions. Okay, so let's say that player number 1 has 2 restrictions, something like this. Okay, let's just start with one restriction. So let's say player number 1 has some restrictions with some other player, so let's call it player number 2 for the sake of simplicity, and this restriction has a length of 5. Then what this means is that only player 1 or only player 2 can play for 5 minutes. Okay, but we know that we always have to play player 1, so we start with s is equal to 1 and we play for 5 minutes. Now why do we do this? So we do this because we are able to do this. Like, we can go for 5 minutes playing only 1, and if we don't do this and if we play 1 and 2 together now, then let's say 2 also have some restrictions, then these restrictions also get affected if we are playing 1 and 2. And so the greedy choice that we are making is, we try to make is, we always try to play with as less people as possible and only include new people when it is necessary. So finally, when playing n is necessary, we will break and end the game. So that is essentially going to be our strategy, and I have already proved this strategy, and the intuitive proof to this is that initially we only play with node number 1 and not with 1 and 2 together, because if we play with 1 and 2 together, then all of these edges will also be getting destroyed, right? All of these edges will also be getting affected. And if we only play with 1, then only this edge is getting affected, and once we are done playing for 5 minutes, then we can play with 1 and 2 together, and then we can start affecting these edges. So in turn, this is definitely giving us more time to play, and I have already proved that. So that's going to be our general algorithm. So let's now write down the algorithm. So start with s is equal to 1. So we start with s is equal to 1, and then we do this until playing n is necessary. So what will we do? So what we'll do is we have a set S. Okay, so we will look at all the edges that go from a node in S to a node not in S. Okay, so we'll look at all of these edges, because if we are playing with all the players in the set S, we have to look at all the edges that will be affected, right? And these are the edges that are going to be affected. So we'll look at, so let's just draw something here to make it sound better. So we have a set S that we are playing, okay, and these are all the edges that we are not playing. Okay, so if we are playing with S, then these are all the edges that are going to be affected. Okay, so then we look at all of these edges and we find the edge with the minimum weight. Let's call it Mn. Find the edge with the minimum weight. Let's call this weight Mn. Okay, so then what we can claim is that we can play with the set S for Mn minutes. So we can play with the set S for Mn minutes, and after the Mn minutes are over, then all the edges that have a weight Mn, let's say that there are two edges that have a weight of Mn, then both of these edges will lose their capacity, right? Because the restriction says that we cannot play with one of the nodes here for more than Mn minutes. So after Mn minutes, both of these edges will be destroyed. So that means we will have to include both of these nodes into our set S. Okay, so then what we'll do is first we play with the set S for Mn minutes, and then we include all the nodes that had Mn as their endpoints. We include all the, so basically we'll look at all the edges that have a weight of Mn. So we'll look at all edges that have weight is equal to Mn, and then we just include the endpoint which is not yet included in the set S, and then expand the set S by including the other endpoint of the edge, right? So that's exactly what we are going to do, and this is the algorithm, and we can say that in every step of this algorithm we are adding at least one new node to our set S. So this algorithm will terminate in at least n nodes, in at least n iterations, right? So instead of n square, I can say that I am playing at most n games. I hope this makes sense. Okay, because in every iteration I am adding a new person, okay, in the set S, and that person is going to be the person that has the minimum possible edge weight with the set S. Okay, cool. So we keep doing this, and finally if we just repeat this process for an infinite amount of time until we find the node n. So break when S contains n. Okay, so when S will contain n, then that means that playing n is necessary at this moment, and then this condition will become false. This condition right here will become false, and then we'll exit the algorithm, right? So yeah, that's the high level algorithm, and that's the solution to this problem. Implementing it was actually not very easy, but not hard either. So let's just have a look at the code, and that will definitely give you much more clarity. Okay, cool. So this is the code. So first we build the graph, okay, and then we keep this set S in the form of a Boolean vector of size n+1. Since n is up to 100, we can do this. Initially the set only contains the element 1 because we are playing with only one. Okay, cool. So what we'll do is we maintain the set S, and now we calculate this Mn. To do that, what we'll do is we'll iterate on 1 to n, and we'll find people that are in S. Okay, so a better way to do this would be to maintain S as a set, but I'm just maintaining a Boolean vector because it's possible to do that as the constraints are small. So we look at the adjacency list of all the people that are in S, and if we find that the other endpoint is not in S, then we say that Mn is the minimum value of Mn comma W. So essentially we found out the minimum outgoing edge, the minimum value of an edge that is outgoing from the set S. Okay. Also another thing that I forgot to mention here is that we also, so after we do this, we have to decrease all the edge weights by Mn, right? So obviously we are playing with the set S for mn minutes, so we have to decrease all of these edges. So we'll have to decrease all of these edges by mn. Okay, cool. So yeah, let's continue. So now we found mn. So if we don't find any outgoing edge, then that means that this particular set that we have is independent. So we can just keep playing with this set. So if that's the case, we can say that the answer is going to be infinite, and then we break out. So this will happen when 1 and n are not in the same connected component. Okay, because if 1 and n are in the same connected component, then we'll eventually hit n, right? Cool. So now we just generate our string using the to-play vector that we have. We'll insert this string into the vector of answers that we are maintaining, and the time is going to be mn. Okay. Cool. So now we'll try to expand the set to-play that we have. So some new people will be added to this set. Okay, so again we'll iterate on the set S, iterate on the adjacency lists. We'll check if the weight of the outgoing edge is equal to mn. If that's the case, then we'll say that the other endpoint of the edge is now going to be included in our set. And irrespective of anything, we'll have to decrease the edge by mn. If the edge is within two nodes that are in to play, then the value of the edge is anyways going to be negative, so that won't harm us. So yeah. So then we go to all the elements that are newly added, and then we say to play of that element is equal to true. So this way we are adding that element to the set S. So finally we'll check if to play of n is equal to true or not, if playing n is necessary or not. If that's the case, then we'll just break out, and then we'll just print the answer. Okay. So yeah, that is the solution to problem D. I hope this was clear, right? I tried my best to explain it as best as I can. So yeah, that's problem D from my side. Let's now look at problem E. Problem E was actually pretty interesting. Let me grab a sip of water. So problem E is actually a pretty nice problem, a very interesting problem. It has a very short implementation, yet you need to think a lot to make this a decent implementation, right? To get to a small implementation, you need to think a lot, and that's what I like about this problem. Okay. Cool. So let's start with the solution. So in this problem, we have n distinct points, and all of these points lie below the line x plus y equal to k. Okay. Cool. So all of these lines have non-negative coordinates, but they all lie in the first quadrant, and they lie below the line x plus y equal to k. And our job is to erase all the points. Okay. So what we want to do is, we have two choices. So the first choice is to draw a triangle, and the second choice is to just erase a point. So let's discuss the second choice first. So in the second choice, basically we have a cost associated with each point, that is c of I. So we'll pay c of I in this operation and just erase this point for c of I cost. Okay. The first thing was that we draw a triangle. So now what we'll do is, in the first choice, we'll choose a coordinate a comma b, which lies below the line x plus y is equal to k, and then we'll draw an isosceles triangle parallel to the x-axis and y-axis, and we'll draw this triangle as long as it hits the line x plus y equal to k. Okay, so in formal terms, we'll choose two integers a comma b, where a plus b is less than k, and then we choose all the points inside the triangle formed by the lines x equal to a, y equal to b, and x plus y equal to k, and all the points which come inside or on the triangle will be erased. Okay. And the cost of this operation is actually going to be the length of the two equal sides of the isosceles triangle multiplied by a number a, which is given to us. Okay. Cool. So I hope this is clear. So obviously now we want to find the minimum cost to erase all of the points. So this is actually a pretty hard problem. So I would say that someone who is rated below 1600 should not really focus a lot on this problem. But if you are trying to upsolve this problem, then that's good anyways. If you know basic knowledge of segment trees or range query data structures, then I think you can spend half an hour or 1 hour to think about this problem and then upsolve it. Okay. So yeah, let's now look at the solution. So I've already copied this nice figure here, which we'll be using to solve this problem. So yeah, the first observation here is that let's just consider that k is equal to 10 here. So if k is equal to 10, let's just draw the line x plus y is equal to k. So the line x plus y is equal to k will be looking something like this. I'm sorry, pretty bad at drawing. And yeah, so here we are. Let's keep a shorter ink and draw this. So this is what the line x plus y is equal to 10 is going to look like. Cool. So yeah, now what we'll do is essentially we'll make a claim, and the claim is that if we draw two intersecting triangles, then we can just draw a bigger triangle to replace those two intersecting triangles. So that's the claim. So let's just write it down somewhere. So okay, so we'll have to go down probably. So problem E. So the claim that I'm trying to make here is that in the optimal solution, we will never draw two intersecting triangles. We will never draw two intersecting triangles, and the proof is simple. We can always replace two intersecting triangles with a bigger triangle covering more points. So it covering more points and costing less. Okay, so that will always be the better choice to for us. So let me just illustrate it as well. So what I'm trying to say here is that let's say we have these two triangles. So let's say we have a triangle like this, and we have another triangle like this. Okay, so we have these two blue triangles. So what we'll do is we'll replace these two blue triangles by a green triangle, and this green triangle will essentially be this triangle. So you can see that this triangle is actually costing less and it is covering more points. So the cost of these two blue triangles is this particular cost plus this particular cost. Okay, sorry. So the cost of the two smaller triangles is actually going to be, so this is 4 and this is 8. So 8 minus 4 plus the cost of this upper triangle is going to be 6 minus 2. 6 minus 2 is equal to 8, and the cost of one bigger green triangle is simply going to be 8 minus 2 is equal to 6. So you can see that one bigger triangle is covering more points and it is costing less, so we'll never have two disjoint triangles. Cool, so I hope this is clear. So let's just erase these triangles. So then in problems like this, when you can make claims like this, then again you should think about dynamic programming. Okay, so that is what we are going to think about. So let's now come to the DP part. So we'll be using dynamic programming to solve this problem. Cool. So what is going to be our DP state? Again, the DP state is going to be simple. So we'll have a DP of y is equal to the minimum cost to erase all points that have y greater than or equal to y. Okay, so if we talk in diagrammatic terms, what I mean is that let's consider y as this number. So let's make it red again. So if we say that this is y, then dp of y essentially means erasing all the points in this particular triangular region. Okay, so then we can say that the final answer is going to be dp of 0, because dp of 0 will mean the minimum cost of covering all of these points. Okay, cool. So I hope that's clear. So yeah, that's how the dp is going to be defined. Now let's try to calculate this dp. For that, let's switch to blue again. Cool. Let me have another sip of water. So yeah, let's see that how we can find out these dp values. So let's say this is the y that we are interested in. So let's say this is the y that we are interested in. So we need dp of y. Okay, so dp of y means all the points that lie in this region, in this triangular region. Okay, so I essentially again have two choices. So the two choices that I have is the two choices that I have are that I will either build a triangle here on this line, okay, on the line y is equal to 1. So now we are interested in finding out dp of 1. Okay, so the two choices that I have is either I will build a triangle on this line having a base on this line, or I will not build any triangle. Okay, uh, so yeah, so if let's just focus on the case when we are building a triangle, and we'll realize that not building a triangle actually comes as a subset of that particular case. So let's see what happens. So let's say we try to build a triangle of length 5. So a triangle of length 5 will look something like this. 1 2 3 4 5. So yeah, a triangle of length 5 looks like this. Okay, so let's say we decide to build a triangle of length 5, then what will happen is that we'll be left with this particular area to cover, right? So we'll be left with this particular area. So this particular area can indeed be divided into two parts. So one is this triangular part, okay, and the other is this rectangular part. So these are the two areas that we need to cover. So we can say that this region is nothing but dp of 7, right? So the minimum cost of covering this region is going to be nothing but dp of 7. We've already proved that there are going to be no overlapping triangles. So we are sure that if we cover this region with a triangle, then there will be no triangle like this, right? Because these are just overlapping triangles. So using that claim, we can say that there will be no triangle which contains both of these regions. So we can solve for both of these regions separately. Okay, cool. So solving this upper region is nothing but dp of 7. But how do we solve this lower rectangular region? We know that there will be no triangles in this rectangular region, because if there is any triangle here, something like this, then it will intersect with our original triangle, and that is something that is not allowed. Okay, cool. So if there are no triangles, then that means we just have to naively erase all of these points using their costs that are given to us. So we just need the sum of costs of all these points in the rectangle. Okay, so that is what we want. Cool. So I hope that is clear. So let me just erase this to get some area. Cool. So let's try to formally write down everything that we have gathered till now. So what we are essentially trying to do is we are trying to draw a triangle, and we try to get some kind of a dp transition. So what we get is dp of y. Okay, so y currently is going to be 1. Okay, so dp of y. So we'll iterate on the length of the triangle that we are drawing. So let's say that the triangle that we draw has length, some fixed length, and we get to a smaller dp of small y. Okay, so we have dp of small y. So here you can say in this example, small y is equal to 7. So this is the dp of small y that I am talking about. Okay, and the leftover region that we have is essentially, first of all, we have this obviously the cost of the triangle that we are building, and the cost of the triangle that I am building is nothing but y minus 1 multiplied by a. So as you can see here, the cost is 7 minus 1, which is 5 multiplied by a, plus the cost of covering all the points in the rectangular region. Now that is the tricky part. How do we find out the cost of? So essentially it is summation ci of all points in the rectangular region. Okay, cool. So yeah, that is what we are interested in. So how do we do that? How can we do this? And we can do this fast enough. Okay, so the naive solution will be very slow. It will actually be of cubic time, because we'll have to iterate on all the values of y, and for each y then we'll have to find out the sum of all the values in this rectangle, and that is something that we are not allowed to do, obviously. Okay, so what we'll do is, the way to solve this is we will maintain a value for each small y. So what we'll do is, for each small y we maintain the sum of the rectangular region. That's what we are going to do. Okay, so let's say that somehow we have maintained these values. Okay, somehow we know this value for each value of small y. Okay, then we can do this transition very easily, right? But the problem here is that once we go from capital Y to capital Y minus 1, so currently we are on y is equal to 1, but finally we want to go to y equal to 0, right? So then we want to update these values, right? We want to update all these sums in the rectangular regions that we have maintained, and we somehow need to do that, right? Cool. So how do we do that? So let's say that somehow we maintain this y, and let's call it I don't know, let's call it sum of y. Okay, sum of y. So then the transitions become simplified, and we can say that the transition is nothing but dp of capital Y is equal to dp of small y plus small y minus capital Y minus 1 times a plus sum of small y. So as we did in problem C, again we can here separate variables containing capital Y and small y, and then we can get to this nice equation, which is that dp of capital Y is equal to minus capital Y minus 1 times a plus dp of small y plus sum of y plus y times a, right? So this is the nice equation that we have, and again we can say that this first part is independent of small y, so this just depends on capital Y, so we can add this up later. So we need to minimize this part. To find the minimum cost, we essentially need to minimize this part. Okay, now how do we do this? So let's say for capital Y is equal to 1, we had all these values calculated with us, and we just used these values. Now we need to somehow update these values for capital Y is equal to 0. How do we do that? Well, doing that is actually not that hard. So what we essentially do is so we are maintaining these values dp of y and y times a and sum of y. So we can say that when we go from capital Y equal to 1 to capital Y is equal to 0, dp of small y is not changing. Similarly, small y times a is not changing. What is changing is this sum of y, and we essentially need to update just this value. Now how do we do that? So I know it's getting a little bit messy, but I'm trying to explain it as best as I can, and I think someone who's well familiar with dp is getting what I'm trying to say with dp and geometry. Okay, so yeah. So what we want to do is we need to update these values of some y as we go from y equal to 1 to y equal to 0 for all the values of small y, and that itself is not a very hard task. So what we'll do is, now we are going from y is equal to 1 to y is equal to 0. So we go from y is equal to 1 to y is equal to 0. So let's say there are a few extra points that we find here. Okay, these are the points that we find. So what we'll do is, if we look at this particular point that we found till now, then this point will be included in sum of small y for all the values of y, right? For all the values of y, it will be included. Similarly, if we look at this point, so if we look at this particular point, then this will be included in the value of some y only for a range of values of y, that is going from here to here. Okay. Similarly, if we look at this point, it will be included from here to here. If we look at this point, it will be included in some y from here to here. So if we just need to update the values of some y, what we need to do is we need to add numbers to ranges. Okay, so if we want to find the contribution, if you want to update the contribution of this particular point, we will just take the range of y from here to here, and we'll add the cost of this particular point to the value of sum of small y for all y going from 9 to 1. Okay, so yeah, that's the job. Not till here, till here. Yeah, so from 9 to 1, from 1 to 9, we'll just add the cost of this point. Similarly, for this particular number, for this particular point that we want to remove, from 1 to 6, we'll have this range, and we'll just add the cost of this particular point to this range, and then we will be able to update the values of some y. Okay, so how do we add numbers to ranges? Well, it's simple. We just use a lazy segment tree. Okay, that way we will be able to do these range updates, and we will also be able to find out this minimum value, right? So we need to minimize this particular value, right? So we can get this minimum value as well, and we can add the numbers to ranges as well. All of this using a lazy segment tree. Cool. So yeah, this is the entire solution. We will just do the updates using a lazy segment tree, and then just get done with it. Okay. So that's the solution. It was actually a pretty interesting problem. There are a few implementation details left, like how to figure out these range and stuff like that. So that's why I was saying that the implementation is pretty neat, but you just need to think a little bit. So let's just have a look at the code to get a better idea. So here's the idea. Here is my lazy segment tree which finds range minimums and adds to ranges. Okay. So what I do is initially for all values of y, I will just have a vector which stores all the points that happen at that y coordinate along with their costs. Okay, and then I will sort them according to their x coordinate. Cool. And then I will first of all build a segment tree which stores all of these values. So the segment tree will store all of these three values, right? So the segment tree will store all of these three values, the sum of these three values. Okay. So we know that for k, dp of k is equal to 0. So the sum of these three values will just be capital A times k. So we'll just update that in our segment tree. And then we'll go from k minus 1 to 0. Okay. And first of all, we'll perform the updates. So what we'll do is the range that we are interested in is I plus 1 to k minus x dot first. X dot first is actually the x coordinate. So you can figure out this math by yourself. It's actually pretty easy. So this is the range of small y's that will be affected by that point, and the increase is going to be the cost, which is x dot second. So that way we'll just update the segment tree, and yeah, so dpi is going to be minimum of dpi and a times minus I minus 1 plus the segment tree queried from I plus 1 to k. Again, this is very simple math. You can verify it from the diagram that I had shown you, and you will realize that it is correct. Cool. So this case that I'm considering is the case when we just draw an entire triangle to cover everything from y is equals to k to y is equals to I. So that's why I'm saying dpi is equal to k minus I times a. Okay. And once we have found out dp of I, then we'll just update in our segment tree for small y is equal to I. So for small y is equal to I, some value is currently 0. So the value is going to be dp of I plus capital A times y, which is small I, right? Cool. So the final answer is going to be dp of 0. I hope this is clear. If it is not clear, I mean, you can code it up yourself, and if you think that the code is not clear, then it is just simple basic mathematics. Figuring out all these ranges is simple basic mathematics. All you need to do is to try and understand diagrammatically from this diagram whatever dp transitions I have written, and you'll get the basic idea if you just focus for 15 to 20 minutes. At least that's what happened with me. So yeah, that's the solution to problem E. So that's all I had in mind for today. Thank you so much for watching, and I'll see you in the next one.